Today, I'll be presenting a talk on one of our recent work, which is statistical learning of NMR tensors parameters from 2D isotropic and anisotropic correlation spectra. So we all know that NMR is a probe of local structure, and by local structure, I mean bond angle, bond distance, coordination number. But when we do NMR spectroscopy, all we end up is with a spectrum in which lies all the way at the start of our journey. And what the next step is to find interaction parameters from these spectrum. And the next step forward is to get structural parameters from the interaction parameters. And by the time we have enough of these structural parameters, or local structure parameters, can we attempt to form a structure? But in this long journey, we're only at the first step, which is this, from the spectrum, getting the local structure, getting the interaction parameter. So what I'm gonna focus here is the spectrum to interaction parameter, but more specifically, the nuclear shielding interaction, which, if you write down an expression, is given in two parts. First is the isotropic part, shown in blue, and the second is the anisotropic part. The anisotropic part depends on the orientations alpha and beta, which is the relative orientation of the shielding tensor with respect to the external magnetic field. The three other parameters that are prominent here are delta iso, which is the isotropic chemical shift or shielding. Then there's zeta, which is shielding anisotropy, and then eta, which is shielding asymmetry. And these are the three parameters that we desire, which makes this problem a three-dimensional. But there are techniques in NMR which we called as separation of interactions, where we can take the isotropic and the anisotropic part and then separate them and correlate them into 2D spectrum. And there are a number of techniques that we can use to do these. Namely 2D 1+ mass, phase-adjusted spinning sideband, magic angle turning, magic angle hopping, magic angle flipping, extended chemical shift modulation, recoupling of chemical shift anisotropy, and variable angle correlation spectroscopy. There's a whole list of experiments that you can do, but the end result is that you correlate the isotropic and the anisotropic part. Now, with the isotropic part removed to its own dimension, we can take a cross-section across one isotropic shift. And then what we get, I'm showing here, is a pure anisotropic line shape. Now, this line shape that I'm denoting with the symbol K sub NISO can be modeled based on our prior information, prior knowledge about the system. We can model it the single site model, or we can have two site, more generically as n site, where f sub I is just the weighting factor and k and iso as a function of zeta I and eta I is the line shape for that particular pair. But when it comes to generalizing this whole equation, we can treat it as an integral of the probability distribution with respect to zeta and eta times the line shapes that you acquire for those parameters. In previous techniques that involved least squares minimization, where you assume a model, which is the probability distribution, then you simulate your spectrum using the integral probability distribution times the line shape, and then compare it with your experiment using some minimization routine like non-linear least squares minimization, and monitor your experiment, monitor your progress. And if you are satisfied with the result, you can finish, and that becomes your probability distribution that you determine. But if not, then you improve upon the model that you initially postulated, and then repeat this whole cycle until you find a satisfactory result. Now, the advantage of this technique is in its mathematical simplicity. It's easy to implement, but the disadvantage is you're constraining or biasing your system based on what model you choose for the probability distribution. The other technique is to use a linear inversion where you take the data and then just perform an inversion and get the final result. The advantage here is that you have no assumption of the probability distribution and it just comes out of the mathematical inversion. But the disadvantage here is in the implementation of this problem. It's harder to invert a spectrum into this kind of probability distribution. But this isn't something new. There has been previous attempts to do this. And in the previous attempts, the parameters, so this probability distribution that I'm showing as a two-parameter, two-dimensional, in previous attempts, the parameter eta was held constant, so which ended up solving for the distribution of the anisotropy. The constraint on eta is unrealistic because we know that eta isn't constant and you can have multiple sites that have different eta within the same experiment. So although this technique is working and has been shown in the past to work, it's not always implementable to all different kinds of experiments and materials that we want to measure. In this work, what I'm going to show is, or in this talk that I'm going to show is how we tackle this problem and when you get a full 2D distribution of anisotropy and asymmetry from a 1D anisotropic cross-section. And in combination with the isotropic dimension from the 2D experiment, we can construct a full 3-dimensional isotropic, anisotropic, and asymmetry parameter distribution for shielding, nuclear shielding tensor. Okay, so now let's get to the linear problem. I've already shown the linear problem in an integral form where f is a probability distribution, k is the line shapes, and s is the measurement. And when I discretize it, it can be written down as, again, in the discrete form as a summation over the probability distribution times the line shapes, which here is a predefined set of line shapes, or what we call as the basis subspectra. And the S is just the spectrum that you acquire. To put it into more of a graphical illustration, we have F, which are the probabilities, and the line shapes, which are what I'm calling as the basis subspectra. And all you have to do is just add the weighting factors times the line shape and then sum it up and equate it to the observed spectrum. Now, if I flip it over and put it into a matrix representation, then all the line shapes are stacked into columns, and that gives you a matrix which is a kernel for this problem. And the kernel is, again, a predefined set of basis subspectra. And the probabilities now becomes a column vector, and then the dot product of these two is the spectrum. So in a simple matrix representation, we can write this equation as k dot product with f equals the signal that we observed, which may include noise. Okay, so one thing that we need to take into consideration when designing a kernel is that we should not allow any two line shapes to be identical. When you do that, you result in a situation where you have parallel bases in your basis set. And you might know this from simple quantum mechanics that we always want parallel basis sets. We never, we always want perpendicular basis set and we never want parallel basis set, because when you have those, we end up in a situation where you have the probabilities in this case, or the amplitudes, that are indistinguishable from each other. Now, the fact that I'm showing this slide, you might find it trivial and maybe comically amusing to be seeing this kind of a slide put up here. But when I show you the next slide here, the way we defined our parameter space, specifically the anisotropy and the asymmetry parameter, we do end up in a situation where you have these kind of parallel basis set. For example, what I'm showing in this figure is, first of all, an entire column, which I'm representing as black dots, are the regions that are not even defined on this grid, because the way eta is defined, when zeta goes to 0, there eta doesn't exist. And the second thing that I'm showing is when eta equals 1, the line on the top, and color-coded into pairs of identical circles are line shapes that are indistinguishable from each other. And that's also very, very well known. When eta goes to 1, you cannot distinguish the sign of zeta. Positive and negative zeta result into the same set of line shape. So that is a problem when we want to construct a kernel. So in order to rectify this situation, what we proposed is a piecewise polar coordinate representation of the two parameters. So what I'm showing here in the figure on the right is the polar coordinate grids, where the anisotropy is actually the radial dimension going outward, and the asymmetry is the angular dimension. But the piecewise declaration is such that the positive half of the triangle, sorry, the upper half of the triangle is positive zeta, and the lower half of the triangle is negative zeta. And the asymmetry parameters is defined such as, if you're along the x-axis, it's 0. And as you go up the angle up to 45 degrees, eta uniformly increases from 0 all the way to 1. And similarly, for the positive anisotropy, if you're along the y-axis, eta is 0. And then if you go down from 90 degrees all the way to 45 degrees, eta uniformly increases from 0 to 1. And in the middle is just a mathematical representation of what I just illustrated in the figure. For the process of implementing this as a numerical recipe, we do end up using the XY, which is just the projection of this polar coordinates on a Cartesian grid, so that it's just easier to work with a Cartesian grid numerically than a polar grid. So from here on, I'm just be referring to them as the XY coordinate grid. Okay, so the second thing that I want to point out here is the number of line shapes that we have to simulate to get to a kernel typically goes to 15,000 sub-spectra, and these are all solid state lines. So you can consider how long will it take to simulate 15,000 solid state spectra. So for that, we actually have another library that we worked on called MR Simulator, which is extremely fast and versatile line shape simulator. And some of the benchmarks that I'm showing here, depending on which line shapes you're trying to simulate, you can do that within milliseconds. For example, the maximum that we go here is 3 milliseconds. So you can simulate thousands of spectra per second with this library. And that is one of the factors why we can use this inversion so efficiently. Okay, next we go into solving the linear problem. Now we've established the linear equation and we got the kernel K. So how do we solve this? Well, the most obvious choice would be to do a the matrix inversion, which is F equals inverse of matrix times X. But the way these kernels are constructed, these are singular matrices, and so the inverse of the matrix doesn't even exist. So what do we do next? There's a way, if you can calculate the inverse of a matrix, you can always trick and calculate a pseudo inverse, which is K dagger, shown here. And the K dagger is calculated using truncated singular value decomposition, where U and V are the unitary matrices truncated to a point R, and S is just the capital S is the inverse of the singular values. So, and the good thing about this is an expression that's easy to evaluate numerically, and so you can get a solution F sub dagger. But when we try to do that, we see something like this. So what I'm showing here on the left is the ground truth solution, the probability distribution that I started with. In the middle is the MAS sideband spectra corresponding to the distribution shown on the left. And on the right is the solution, the TSVD solution F sub dagger. Now at a glance, you can see that the solution is nowhere close to what we started with, but we have a really high amplitude close to what we would expect. But there are amplitudes all over the place, including negative amplitudes, which would result in negative probability distribution, which is unrealistic. So straight away, this kind of a solution will not work. What we need is a more constrained solution. And that brings us to regularization. So a regularized solution, F tilde, is given as the argument that minimizes the sum of mean square error and a regularization term subjected to constraint that F is always greater than or equal to 0. The symbol that I'm showing here is called the L2 norm. Oops. It's called the L2 norm, which is given as a L2 norm square of a vector X is the sum of vector element square. So from the TSVD solution, we saw that there were amplitudes all over the place. So what we needed is a sparser solution. So what the best known regularization term for a sparse solution is the L1 term, which is lambda times the one norm of F. And the one norm of F or a vector is given as a sum of absolute values of vector elements. Now, when we apply this regularization, what we see is a significant improvement in the solution that we get. We have no negative amplitudes, and the solution is approximately centered about the desired positions. Now, when we say sparse, sparse is actually a relative term. I can take the same ground truth distribution, and if I bin it on a coarser grid, I'll get a sparse solution. But if I take the same distribution and bin it on a high resolution grid, the solution, the distribution is no longer sparse. And that is what the problem is with the L1 solution. So here, what I'm showing is a 20 by 20 coarser grid where the solution is closer to the ground truth solution. But when I increase the resolution of the grid to 50 by 50, the solution is no longer what I expect, but the solution is still sparse, which is what the L1 term is promoting. To fix this, what we can do is add another regularization term, which is an L2-ner. So here the regularization is alpha times the 2 norm square plus lambda times the 1 norm, which is also commonly known as the elastic net solution. So what this does is L1 promotes sparsity, but L2 terms promotes grouping of closely related amplitude. And depending on the relative contribution that we add into the regularization, we can either make a solution sparser or make the solution more L2 dominant. So what I'm showing in the solution here is on a 20 by 20 grid, if I take the ratio lambda over lambda plus alpha, it's 0.7, which means that the solution here is 70% dominated by the L1 term, and it's 70% on the side of a sparser solution, which is what we saw with the L1 solution too. So on a coarser grid, the solution is more sparse. When we go to a high resolution grid, what we see is the same lambda over lambda plus alpha factor is about 0.25. So here, only 25% is the L1 term, and the signal is dominant by the L2 term, which promotes grouping of the signal. So with the combination of the two, the elastic net solution, we can solve the problem of the solution being dependent on grid. Now we see a consistent solution across all grid sizes. What problem that we see here is now these solutions have sharp edges, and some of them may also have isolated spikes. So to remove these kind of issues that we see in this solution, we can use something called a smooth-LASSO, which is again a combination of L2 term shown in blue here and an L1 term, which is as we've seen before. Now, the only difference in the L2 term is instead of taking the 2 norm of the vector itself, the vector f, we multiply it by a smoothing matrix. So J sub x and J sub y are the 2 smoothing matrices that actually smoothes the solution along the x direction and along the y direction. And they are given as a Kronecker product of the first difference matrix A, shown here in the matrix from, times the identity matrices. So with this regularization in action, what we see is actually the solution that's smooth, and also we don't see isolated spikes showing, which is more commonly the case when you have more noise in the spectrum. So now we have a solution that's consistent across grade and is smooth. So, and this is the regularization that I'll be using for the rest of the presentation. So I've been showing these regularization terms, and there were 3 factors that were always being used, which are the alpha and the lambda parameters. And most commonly, they are very difficult to find when you are trying to, like in most algorithms, the alpha and lambda parameters is kind of hard to pick, like what to choose for these values. So we try to overcome that. Like it's not what I am supposed to be providing to the solution, but the solution will find and learn what is the optimum regularization parameters that should be applied. And this is all done by a 10-fold cross-validation. So the figure that I've shown here is actually the cross-validation error. The contours is a cross-validation error. And the most optimum alpha and lambda parameters are the one that actually minimizes the cross-validation error. So all of that is done by the algorithm itself. And so we, as a user or as this scientist, don't have to worry about putting these numbers in. Okay, so now let's get to the test cases in using the smooth-LASSO regularization. This first thing is, well, can we invert noisier spectrums, or in this case, sideband spectrums? So here, the anisotropy is actually recorded at the magic angle. So you see the anisotropy broken up into the sideband patterns. On the top is a spectrum with a lower noise of standard deviation 0.001. And in the lower half, we have a spectrum with a higher noise of 0.02. And what I'm showing here on the top is the noise after you do the regularization. So that's actually the residuals. And on the right is the inversion, the result of the inversion using smooth-LASSO regularization. And what we can see is if you have a lot better signal to noise, you get a better inversion. And if you have higher noise, then the noise actually manifests itself into the solution, giving it a broader distribution, which adds to the uncertainty in determining the distribution itself. And the same thing can be done if we are doing another kind, which is the magic angle flipping experiment, in which you determine the anisotropy at 90 degrees instead of magic angle. So it's the same representation here. The upper one is done at a lower noise level, and the lower half is at a higher noise level. And what we see is, again, a consistent solution with respect to the inversion. Now, when it comes to sidebands, we also have to consider like how many sidebands do we need in order to get a desired inversion, the accurate inversion. So what we find is you should have at least 12 sidebands in order for the inversion to accurately predict the distribution, the underlying probability distribution. If the number of sidebands reduces below that, then there's enough information loss, because MAS is a technique that gets rid of anisotropy. And the first parameter that you lose, or the first uncertainty that you develop, is in the asymmetry parameter. And as you can see, it gradually increasing the spinning speed or decreasing the number of sidebands, the asymmetry is extended to the entire positive plane. And if you go even further below to say 5 sidebands, then not only just you have uncertainty in the asymmetry parameters, but also in the anisotropy parameter itself. And in the limit that you hit a sideband equals, number of sideband equals 1, then the uncertainty goes to the entire surface of this XY plane. And the results that we see in this one slide illustration is actually consistent with the findings of Hutchinson and Emsley, where they do reliability of the shielding tensors based on spinning sideband. Okay, so up till now, what I've shown is just one kind of a distribution, a bivariate normal distribution. But there are other distribution types which are commonly used for solids, which includes the check distribution. And what I'm showing here are the two cross sections, one for 90° and one for magic angle. And on the right is the inversion of these, which gives a same heart-like shape for the check distribution. The other kind of distribution that's commonly in use is the extended check distribution, which similarly done for 90° and magic angles result in a exact and proper inversion. Okay, so up till now, what I've shown is a lot of illustrations on the validity of the inversion process itself. But now what I'm going to show is the application of these methods to non-crystalline solids. Specifically, I'll be showing the silicate classes. One thing that we need to know about silicates, just a brief summary, is that silicates have these species called the Q label species, where Qn, where n can go from 4 all the way to 0, is the number of bridging oxygens. So for a Q4, you have 4 bridging oxygens. Q3 has 3 bridging and 1 non-bridging oxygen. And it goes all the way till Q0, which has all 4 non-bridging oxygens. And depending on what species you see, they have a different anisotropic line shape patterns. So if I want to put these line shapes on the XY region, XY grid, then the Q0 and the Q4 have the least anisotropy, which you can see will be around the origin. The Q3s will be along the y-axis. The Q2s will be somewhere in the middle, and the Q1s will be on the opposite side, along the x-axis. So now the experiment that I'm showing here is for a magic angle flipping experiment, where you see a 90° anisotropy along the x-axis or the horizontal axis, and the isotropic chemical shift is the vertical axis. So when doing the inversion, we take one slice, the one anisotropic slice, and do an inversion, get a 2D plot, which becomes one surface of this 3D volume. And to construct the entire 3D volume here, what we do is just do the inversion line by line across all these isotropic shifts and then construct this distribution. So what we see in this is spectrum is a Q4 and a Q3 site, which we see completely resolved in this 3D distribution, where we see Q4, which is centered about the origin of the XY plane, and also centered about minus 110 ppm. And a Q3, which is centered about minus 90 ppm isotropic shift, is shifted towards the x-axis, which is just also where we expect the Q3s to lie, which is along the y-axis. Now, if you take a look at the projections that I'm showing onto the XY plane, then we will see that the Q4 has a heart-like distribution, which is a distribution consistent with a check distribution, and a Q3 is more like an extended check distribution. So what we find is that the inversion method learned these advanced distributions like check and extended check without ever knowing about these distributions. Next, what we can do is just quantify the probability, the statistics of these distribution, since they are separate in this 3D plane. And what we see is the population. We can calculate the population and the chemical shift, which is also consistent with the original work where this experiment was done. And similarly, for the Q3, we can calculate the statistics for population, isotropic chemical shift, mean anisotropy, and mean asymmetry, all of which is consistent with the previous work. So we have a technique that can give you not only the distribution, but a statistical analysis of, we can also perform statistical analysis on these distributions. So next, what I'm going to show here is, it is actually a 2D plot of the same distribution, except what I've shown here is the isotropic X and Y. We can convert this into isotropic, asymmetry, and an isotropy parameter. And then what I'm showing here is actually projection for that 3D distribution. So you have isotropic shift and shielding anisotropy. So here, what we see is more of a finer structural details into the structure. So a Q4 is shown as a bimodal distribution, which is near symmetric and near symmetric about eta equals 0. And if you are familiar with the check model, then you will see that this is a classic check-like distribution when you plot that on the anisotropy scale. So what we see here is the anisotropy actually increases as you increase the chemical shift, which is something that was already reported in the original paper by Baltus-Berger, and it's attributed to the fact that there are Q4s that are surrounded by all 4 Q4s, and that there are Q4s that are surrounded by Q3s. So as you increase the isotropic chemical shift, you also increase the anisotropy because the Q3s are more susceptible to disorder. But there's also Q3 site here, which also have this correlation, a negative correlation between Q3 isotropic shift and Q3 anisotropy, and a dependence on the anisotropy width with respect to the chemical shift. Now, this is something that wasn't reported in the earlier paper, but we can now see them, and there are more investigations to be done in order to quantify what exactly does that mean in terms of the structure. And we can do this for all different kinds of composition, glass composition, as I've shown for 4 different cases here, either from a MAF experiment or a magic angle turning experiment. And all of them exhibit a Q4, which is symmetric about 0, and a Q3, which, and interestingly, you find the Q3s have different correlation. And there's a lot of data mining that can be done in this particular slide. But in the interest of time, I'm just gonna focus on the Q3, specifically the projection of all these Q3s. So if I isolate Q3 projections from all these 4 different compositions and then plot them together in a single slide, then we can see so what Daniel found in his paper in 2018 was that the mean anisotropy can be represented as a linear relationship between the silicon bonding oxygen and silicon non-bonding oxygen distances. So with that equation, what we can convert a shielding anisotropy distribution into a silicon non-bonding oxygen bond length distribution, which is also consistent with what we find in the literature about for the mean position of the silicon non-bonding oxygen bond lengths. So, and that is the second step from taking the parameter distribution into a structural distribution. So, and so up till now, what I've shown is a distribution that only had two species, a Q4 species and a Q3 species. But here is an example of calcium silicate class where you have all the species present in this. So starting from A, where you see a Q4, then moving on to B, where you see a Q3, and then C, where you have a Q2, and then to the D, where it goes down to a Q1, and then at E goes back to a Q0, and this is all consistent with the mapping that I've shown earlier. In the end, I would like to present this a library that we wrote for this particular inversion, which is called NMR inversion, which is a library written in Python for inverting isotropic and anisotropic spectra. It's available on GitHub for free and it's easy install using pip, and the library is extensively documented on Read the Docs. To show you a quick example, here is the library itself. And what we can see here is all the examples that I've shown are, I haven't covered all of them, but we have every single example shown here. And this is an inversion of potassium magnesium disilicate, tetrasilicate glass, and where we show the entire script of how you can get the data set, focus the data onto the desired region, set up the inversion kernel, generate the kernel, and then optionally compress the data, and then set up the inversion problem, which is smooth-LASSO cross-validation, and then plot a cross-validation plot, get the optimum alpha and lambda parameter. And this is just the residue from what we see as the optimum solution. Then visualize the optimum solution, which is again a Q4 and a Q3. And then we can separate these out into individual voxels and then do a statistical analysis of these voxels. And then we can have Q4 and Q3 statistics. We can go further on and convert that into a more conventional isotropic zeta and eta. Again, if you're familiar with check distribution, you will see this eta zeta plot as really consistent with the check distribution. And all of that done within 90 seconds. So it is a really fast library for these kind of analysis. Okay, and to conclude, we have a robust inversion method for determining a 3D tensor parameter distribution. And the inversion shows potentially revealing more correlation and potentially into more structural insights about the material itself. And we have an open source library that can do all these analyses. And in the end, this approach can be extended to other interactions in a matter of just changing the kernel. So on the right, what I'm showing here is the inversion of MQMAS spectra, where you have a rubidium nitrate spectrum, and you can invert those into their respective CQ and eta, or in this case, I'm using X and Y, that can be mapped back to a CQ and eta distribution. And with that, I'd like to acknowledge the Grandinetti Lab, J.H. Baltisberger, and National Science Foundation in Ohio State, a National Science Foundation for the funding. And with that, I am ready to answer your questions.
Now we got a few questions for Deepansh. The first one is from Vincent Sarro, Kenya. The question is, very interesting work. You tried first derivatives on the F term in your penalty term. Did you also try the second derivatives on the F term that is typically used in the inverse Laplace transform for relaxation times distributions?
Yes, we did try the second derivative, but we didn't see much improvement from first to the second derivative. So we decided to stick with the first derivative.
All right, and the next question is from Dominic Massiot. The question is, when treating two-dimensional experiments, do you have a, where's the question again? Here. When treating two-dimensional experiments, do you have a regularization on the isotropic shift dimension?
At the moment, we don't have any regularization on the isotropic shift. That is something that can be added, but the issue comes with the resources at hand, because that regularization creates a massive kernel, which currently my personal laptop cannot handle. But yeah, that can be done, a regularization on the isotropic shift.
Great. So we have another question from, I assume, George. The question is a really beautiful talk and impressive work as well. I did not get the improvement going from LASSO to smooth-LASSO. Can you please come back to that?
Okay, so there's a whole series here. So the LASSO experiment, not the experiment, the regularization that we have here, is actually, we'll always choose the most sparse solution that you have. So which in turn makes it as a grid dependent. So when you, if I take the same ground truth solution and then bin it on a coarser grid, the distribution that I get is sparse. But if I take the same distribution and then bin it on a high resolution grid, then that distribution is no longer sparse. So what you see here in the LASSO term is, depending on the grid size, you still get a sparser solution, but that solution is not consistent with what our original probability distribution was. So then we came to the elastic net problem, which is to add the L1 and L2 term, which makes it uniform in the sense that the solution is consistent across grids. So if you have a low resolution grid, then the term is L1 dominated, and a high resolution grid, then it's L2 dominant. But now the problem here was that you have these sharp edges and then some unwanted isolated spikes. And that's when we used a smooth-LASSO, which is still a combination of L2 term, which entire thing here shown in blue is an L2 term, and then this is an L1 term. But the L2 term has a smoothing penalty applied to it, with JX smoothens it along the X and JY smoothens it along the Y. And that's what the smooth-LASSO solution is. We actually didn't come up with a name. It was already published, this kind of regularization. So that's the difference between LASSO and smooth-LASSO distribution. Sorry, regularization. Does that make sense?
Yeah, I guess, I mean, we really couldn't do these interactions here, but if you have further questions, I guess you can contact the Deepansh directly. So let's probably move on to the next question, which is posted by Jay. On the rubidium nitrate data, you end up with mostly 3 sites, which is what exists in the crystal. But do you know why what is that? There are extra regions of non-zero probability artifacts, maybe impurities. You can.
Yes, that's a really good question. So yes, rubidium nitrate here has because this is all, I should mention, this is still a work in progress. This is not a publication figure here. So, but rubidium nitrate has 3 sites. And what we see here is 3 most distinct, but there's extra blurriness all around the solution. That is indeed an artifact, but that's not the artifact from, so that's actually an artifact coming from the fact that the amplitudes of these line shapes are dependent on crystalline orientation. And the kernel that we are using is assuming an ideal line shape. So when you can use an ideal line shapes and you have distorted line shape in experiment, you get these unwanted intensities. So what we are working at the moment in the lab is to refine these kernels so that it actually represents the conditions under which an experiment was conducted. So with that correction factors, we will get rid of all these unwanted intensities, and then you'll only see 3 sites in this inversion.
Okay, the next question is from Professor Geoffrey Bodenhausen. Can you handle partly overlapping families of sidebands corresponding to different isotopic shifts?
Can you say that again? What's the question?
I think you can also view the text in the Q&A channel. So the question is, can you handle partly overlapping families of sidebands corresponding to different isotopic shifts?
Yeah, I'm trying to find the question here. Can you handle?
I believe.
You know, Deepansh, I could step in. I think Jeffrey's just asking if you have a distribution of isotropic chemical shifts and sidebands, how do you do this approach? So you have, the kernel has to get bigger, obviously, right?
Yeah, but so that would be a case of 1D experiment then to 3D experiment. What we are talking here is you have already separated the isotropic shifts from the sideband dimension. So it's kind of 2D math or past experiment. If you have overlapping isotropic shifts and sidebands, that will be a 1D experiment to a 2D, and that will result in a massive kernel. Again, it's doable. I'm not sure how well defined or how accurate the solution is going to be, because now your solution would be a lot more, has to be a lot more regularized, because now you're going from 1D to a 3D distribution. And I don't think my computer can handle that kind of a massive matrix. But yeah, I don't know if that's going to work, but theoretically, you can use the same kind of setup to get to that solution.
The next question is from Joseph Maximilian Jurdis. Sorry if I mispronounced the name. Great talk. Can you comment on kernel size or inversion dimension sizes, especially when calculating the inversion on very broad line shapes?
Right. So the size of the kernel actually depends on how fine your grid is. So usually what we do is kind of apply a super sampling scheme. So which means that we will construct a very high resolution grid. So for example, when I was showing here, a high resolution grid can typically take around 15,000 line shapes or spectra. And what we do after that is we downsample it to around 600 line shapes. So what it does, so here, like this is a high resolution grid, 125 by 125, and then we downsample it to 25 by 25 grid for actual computation. What this does, it actually maintains the integration, which is because my high resolution grid is sampled close enough so that the integration converges, but I don't have to solve the solution on this grid. if that answers the question. So usually for all these experiments, the inversion dimensions were 25 by 25 to 32 by 32, and super sampling schemes were more than 128 by 128.
We got another question. The attendee could not use the Q&A, so he posted in the public channel. Michael asked, am I correct in thinking your solutions are not unique, but your regularization gives a solution which is smooth and clustered if possible? What
Yes.
if you have, yeah, go ahead.
Okay, so yes, the fact is all these are ill-posed problems. So for one, there is no solution. What we can get is a near solution. So we can approach the right answer, but we cannot get to the right answer. So that's the hard truth of the problem itself. And the second thing is the regularization can get you close to the solution, but depending on what regularization you choose, you can end up with different kinds of solutions. So what we are choosing is a regularization that is consistent to what is publicly believed to be a likelihood for a probability distribution. For one, it's smooth. So you can have just arbitrary spikes in probability distribution. And two, if there are more than one just like spikes, then they have to be kind of smoothened out. So this is, again, based on what we believe is, or what actually the literature believes is the right for choosing a probability distribution, but it's in no respect a unique solution.
Okay, the next question is also from Dominic Massiot. Would it be possible or efficient to consider the principal values of the tensor instead of ISO or non-isotropic?
Yeah, you can consider. It would be, so the reason why we choose ISO and ISO-eta, it's because it's much more easier to proceed with the problem in this frame, just because one of your experimental dimension is isotropic. You can do principal components, but then you just made the problem harder because now principal component is actually mixing the two isotropic and the anisotropic together. So instead of taking 1D slice and inverting into a 2D spectrum, you made the problem even harder. Now you're going from an entire 2D spectrum to a 3D distribution. So it's just there's mathematically it's the same, but it's just one is a lot easier to implement than the other.
Another question from Brennan Water. Great talk. If you have a single site, would you ascribe the width of the probability distribution to parameter uncertainties? Then for real parameter distributions like in glasses, can you determine uncertainties on, for example, average zeta?
Yeah, so the uncertainties that we get is actually manifested into these distributions itself. So if you remember the example that I've shown for, in the case of sidebands, yeah, so like this is one of the examples. These are all uncertainties. One of the uncertainties coming from the fact that you're removing a part of an isotropy that you're trying to determine. So that leads to these uncertainties. And the second part of the uncertainties comes from the noise, which I've shown here. If you have more noise, you get more of these uncertainties, but that's true for any way, or even the least squares problem. So, and if the question is, can we determine the extent? I would have to say at the moment we don't have that ability to say what part of this is zeta and which part is the uncertainty, because all of them lumps in together. The same thing holds if you have contaminations, or well, contamination in terms of the kernel. So if I have a kernel which is only sampling for like CSA sidebands, but you have dipolar sidebands that will also lead to broadening or unwanted peaks. So yeah, so that's something that we can quantify at the moment.
Okay, because of time, there are 2 more remaining questions. I suggest that we will finish those 2 questions, but maybe no more questions, just for the sake of the time. So the first remaining question is from Demetrius Sakilarios. Sorry if I mispronounced the name. Very nice presentation. Is there an optimal isotropic and isotropic 2D experiment that provides most robust inversion? Does this depend on the sample tensor distribution?
So we've tried with both sideband, like 2D isotropic and sideband dimension and a 2D isotropic and a VS or magic angle flipping dimension. And we got to the same result. So it didn't really depend on which experiment you did, as long as for the sidebands, you have enough sidebands for you to resolve the anisotropy. Both experiments will give the same result in the end.
All right, the last remaining question from Zhuoren Wang. Impressive talk, thanks. There is one point I didn't quite get. When you build your set of sub-spectra, you discarded identical spectra with different CSA parameters. Then to me, it seems that the distribution you find may have some ambiguity. Can you explain again on that part?
Yeah, so that is something that's inherent into the problem itself. This is not something which is unique to this set of inversion problem. So the way this eta, so here. So the way zeta and eta is defined is that you cannot distinguish a positive zeta from a negative zeta when your asymmetry is 1. And that's true for any approach, even if you're using a least squares fit. What we are doing in this method is we are taking those 2 points that are identical and then just having them share the same coordinate system, so that in the inversion problem, we create a kernel that is that has a higher rank. So the more rank deficient the kernel is, the more uncertain the solution becomes. And I think, but yeah, that's all of it. Yeah.